Hello students, now we are in a state to discuss a very important theorem in statistical mechanics and modern physics as well, which you are already familiar, known as the Equipartition Theorem. You have studied about the Equipartition Theorem, and it's one of the statement in thermodynamics classes, or when we discussed about the kinetic theory of gases in your higher secondary physics syllabus. So in this lecture we are going to see a more generalized form of the equipartition theorem. We will state the theorem and then we'll try to prove that theorem. So let's first try to understand the most common way of stating equipartition theorem, and maybe we'll try to understand what actually it means. So the equipartition theorem, as the name itself says, is telling about the distribution or the sharing or partitioning of energy of a system amongst the particles of the system, or we can say amongst the various degrees of freedom of the system. We do clearly have a meaning of what is meant by the degrees of freedom of a system. So for example, let me make some examples. You consider a particle, say a free particle, which is moving, which is constrained to move along, say, x-axis. So it is constrained to move along x-axis. It's a free particle, and you know a free particle is possessing only kinetic energy, right? So since it is constrained to move along the x-axis, its velocity will be purely along x direction. So v will be equal to vx, or it will be equal to x dot. So what about its kinetic energy? Its kinetic energy, I can say E will be equal to simply what? Okay, I can say that it will be equal to half, in terms of that one, half m x dot square. There is no y dot and z dot, right? So it has got only one component of kinetic energy, right? Now if another particle is free to move in a plane, right, means it is say it is free to move along two directions. Okay, two directions in the sense that it is free to move along, okay, the plane containing x and y, say. So what about its energy expression? So certainly you know that its energy expression will be having, okay, so it will be equal to, simply we will write half m, okay, the velocity square. So velocity square will be x dot square plus y dot square, right? Okay, and if the particle has got freedom to move in all the three dimensions, so certainly we will be having the energy, kinetic energy expression still modified. It will be half m times x dot square plus what? Y dot square plus z dot square. So all the three okay, coordinates will be there. So it means that here in the first example, the particle had got only 1 degree of freedom. In the second example, the particle has got 2 degrees of freedom, and the final example, the particle has got what? The 3 degrees of freedom, right? That is about the degree of freedom of the particle as far as okay, what you call the axes of motion are concerned. Now so what actually the equipartition theorem says is that the available energy of a system is partitioned or shared equally among the various degrees of freedom of the system. See, okay, you know that for example, we take the energy of the particle that is equal to 3 by 2 n kBt, right? We already seen that for a classical ideal particle it is equal to 3 by 2 n kBt for n particles. So instead of that, for one particle it will be 3 by 2 kBt, right? 3 by 2 kBt. And if you think of why this 3 by 2 kBt, you can just understand this one as 3 into half kBt. This is the way in which it is interpreted. 3 into half kBt. And so you can see that why this 3, because a single particle moving in say a volume V has got 3 degrees of freedom. As I told you, like it can move along x-axis, move along y-axis, and move along what? Z-axis, or any linear combination of these things, right? So we can understand or we can comprehend this result E equal to 3 by 2 kBt as what? 3 times half kBt. And what is this 3? The 3 corresponds to the degree of freedom. So if I just represent 3 by F, so we can say that it is equal to F times half kBt. Or we can say that each degree of freedom contributes. That is, putting in other words, each degree of freedom of a system contributes how much energy? Half kBt energy to the total energy of the system. So we can say that available energy of the system is shared equally among the various degrees of freedom. Means each degree of freedom will be contributing equally to the total energy of the system. Or putting in other words, it can also mean that there is no any preferred direction of motion as far as a particle is concerned. There is no any preferred direction of motion for a particle. Means it doesn't have any partiality. Okay, preferred direction or orientation. Okay, direction of motion for a particle. For any particle in a system. Okay, so it means that nowhere you can expect that the entire energy will be along x-axis. Okay, the entire energy is due to the motion along y-axis. No. Okay, so the probability that a particle will move along x, y or z, all these things should be equal. So that actually is put in another way, that the energy is partitioned equally among various degrees of freedom. Means the particle doesn't have any preference of any direction as far as its motion inside a container is considered. So that is the simplest idea. So it's also the same equipartition theorem. Maybe that's a way in which you have learned in your higher secondary classes, that each degree of freedom contributes an energy equal to half kBt to the total energy of the system. Right now, in our topic, we will be discussing a more general form of the equipartition theorem. So usually the equipartition theorem is stated as a generalized statement, which is known as generalized equipartition theorem, otherwise known as Torments equipartition theorem. And there is a much a specific version known as what? The Boltzmann's equipartition theorem. So we will discuss both the equipartition theorem one by one, and as per the need we will be just going to one of these. Okay, so first we will discuss the generalized equipartition theorem, right? And this equipartition theorem becomes the basis of many other theories. Especially it will help us to understand see the distribution of energy of particles in a system. Sorry. So we will first go to the generalized equipartition theorem. So that is usually stated mathematically. The generalized equipartition theorem is stated mathematically as a relation between the expectation value and the temperature of the system. So just introducing, so it states that mathematically, it states that the expectation value, expectation value of a quantity which I am going to write as xi times dou h by dou xj, expectation value of the product of xi with the partial derivative of the Hamiltonian of the system with the xj is equal to Kronecker delta ij, we have taken I and j, so I have to take the same indices, Kronecker delta ij times kBt. Kb is the Boltzmann constant. So this expression, mathematical expression, is what is known as the generalized or Torments equipartition theorem. So here, where what is this xi and xj? This xi and xj are any of the 6n phase space coordinates. 6n phase space coordinates, or we can just say that generalized coordinates. The generalized coordinates and generalized momenta. Coordinates means coordinates and momenta. Generalized coordinates or phase space coordinates. Phase space coordinates. It means that that is xi can be qi, xj can be qj, or it can be pi, it can be what, pj. Means, okay, for a system consisting of n particles, there will be 3n values for this q's and 3n values for what, the p's. So that altogether there will be 6n, okay, just coordinates as well as momenta, which are regarded as the 6n generalized coordinate which span the phase space, right? So we say that the phase space for an n particle system is 6n dimensional because it is spanned by 3n generalized coordinates and 3n corresponding or conjugate generalized momenta. Okay, so here xi and xj stands for any one or any of the 6n coordinates or momenta. Okay, for example, xi can be p1, xj also can be p1, or xi can be equal to p1 and xj is equal to q2. Okay, any combination. So there are so many combinations there. We will see its relevance in the coming discussion. So this is exactly this particular mathematical statement is what is known as what? The generalized equipartition theorem. So how do we state it? We can say that the expectation value. So remember, this is nothing but the expectation value. Okay, see, we are concerned about the expectation value of physical quantities. Okay, in the case of ensembles, expectation value of that quantity. Okay, of the quantity xi times dou h by dou xj. This is the way. And of course, needless to mention, h in the expression is the Hamiltonian of the system, which is a function of what? The q's and the p's of the system, right? Now let's see how to prove this particular mathematical statement, and the proof will throw some light on what's the meaning of these terms, right? So we begin with the basic definition of the expectation value of any physical quantity f in canonical ensemble. So in canonical ensemble, I'm writing simply CE, the expectation value of a quantity, so we had introduced about the expectation value of a quantity while discussing ensemble average and time average, the difference between ensemble average and time average. So in ensemble, the average that we are depending on is known as ensemble average. Otherwise, it is mathematically equal to the expectation value of the quantity. Okay, so the expectation value of any quantity, any physical quantity that is of interest for us, say EF, quantities we are denoting by EF, is given by, any quantity is given by, so the expectation value or the ensemble average of the quantity F is given by, F is equal to, it's written for a classical system. Okay, for a classical system, it is given by integral F into e raised to minus beta h d omega. You know what is this e raised to minus beta h? That actually is the density function rho. Okay, divided by integral e raised to minus beta h d omega. So this is the assuming, if you, this is the expression for the expectation